Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, we are starting our second lecture on the course. If you recall, in the previous lecture we had discussed about the rocket equation, which is known as the Tsiolkovsky's equation, and there we found out that the incremental velocity delta v is going to be equal to V j ln mi by mf, where V j was defined as the efflux velocity, mi was the initial mass of the rocket, mf was the final mass of the rocket. And we know that in order to give the high velocity to the vehicle, we need to give in incremental order, and that is why this delta v incremental ideal velocity is an important equation. Now, we should also appreciate that this incremental velocity cannot be given in one stage or single stage. If it can be given, it is of course beneficial, like single stage to rocket or even in two stage SSTO, single stage to orbit or two stage to orbit. Those are like efficient vehicle, but in reality it is very difficult to give a high incremental velocity at once. Instead, the incremental velocities are given in stage wise. That is why there is a concept called multi-staging. So, we will talk about that multi-staging here briefly, because you have already learned that thing in the previous course. Now, we have also discussed about the mass ratio of the rocket, which is defined as the final mass divided by the initial mass. Then we have also talked about the various mass fractions like payload, structural and propellant mass fractions, and we have rewritten the delta v equation in terms of those mass fractions. Now, if you talk about the multi-staging in a rocket is the design concept, where we are making the velocity increments stepwise or stage wise. So, here actually the strategy is to make ascent missions more efficient by dividing the total rocket into number of sub rockets called stages. Typically, each sub rocket is a complete rocket by itself, and at the end of the burnout, the shell and other inert mass are discarded from the rocket. Now, after each stage is over, the second stage will start and keep running. It is going to provide the velocity increment. Now, also if you can recall in the previous courses or in your basic courses, that there are rocket at the bottommost stages where they are tied up with the main rocket, or we can say the booster rocket. So, if this is the booster stage, there are some rockets which are tied up with this booster stage. These are called clustering of rocket. So, we can call this as parallel staging. Some way you can say it is a parallel staging. Now, the multi-staging is done like the serial manner. So, this is the concept of multi-staging. So, this is the first stage, this is second stage, and this is third stage. So, the total velocity increment will be like velocity increment provided by the first stage plus velocity increment provided by the second stage plus the velocity increment provided by the third stage. Now, one can actually derive a generic equation considering the n number of stages, and you can write down the velocity increment, total velocity increment as V j 1. So, we can just writing the rocket equations what we got already in terms of the mass ratio, which is going to be like 1 by R m 1 plus V j 2 ln 1 by R m 2 plus V j 3 ln 1 by R m 3 and so on, V j n ln 1 by R m n. Okay. So, this is like a generic way of writing. One can actually simplifying it by considering the efflux velocity, that V j 1 equal to V j 2 equal to V j 3 equal to V j n equal to average V j, and one can write this in terms of the following equation, which is like average efflux velocity ln 1 by R m 1 into R m 2 and so on, 1 by R m n. Okay. One can further simplify this by considering the final mass of the first stage is going to be the initial mass of the second stage, the final mass of the second stage is going to the initial mass of the third stage and so on. So, if we do so, we can get delta V equal to average efflux velocity ln m I 1 by m I n. Okay. So, this gives the ratio of the this should be the m f n. So, this will give the ratio of the initial mass of the first stage to the final mass of the last stage of the rocket, or you can say it represents the overall mass ratio of the rocket, which is going to be equal to one can write this as V j ln 1 by, if we just consider that this is to be like a single mass ratio R m. So, this is going to be to the power n. So, it will become n V j ln 1 by R m. Now, I am following these equations from one of the textbooks given already in the course curriculum, which is rocket propulsion book by Professor Ramamurthy. So, one can refer to it for more details, even the NPTEL video lecture is also available. So, these are just a revision of what we have already learned. Now, if you recall, we had already told ourselves that in the delta V equation or the ideal rocket incremental velocity equation or rocket equations, the V j or the jet velocity was an important parameter. So, can we just spend some time and look at what are the influencing factor of this V j. But before going to that, some of the assumptions we should remember, or we should recall in terms of the ideal rocket. So, some of the assumptions we generally follow for ideal rocket. Now, why we really look at these assumptions? Because the concept of ideal rocket is useful, because the relevant some of the basic thermodynamic principle, we can express those principle in a simple mathematical relations, and of course, that will help us to derive certain equations in a simpler manner. Some of these equations will actually describe the quasi one dimensional nozzle flow, which we always consider. That is of course an idealization and simplification of 3-dimensional flow, and of course, it involves the 3-dimensional equations and real aerothermomechanical behavior. However, these relationship will give us a starting point for the designer to understand how we can represent the flow behavior or the overall aerothermochemical behavior in terms of simple mathematical relations. Doing so, the overall error, if we can see, it will not be more than like 5 to 6%. So, it will be a good estimate to begin with these ideal rocket assumptions with the simplified equations, and we can actually get some performance parameters which will not be that much off from the actual performance parameters, maybe between like 1 to 6%. So, let us talk about the various assumptions involved for the ideal rocket concept. So, the first one, we consider that the working substance, or sometimes we say the working fluid, the working substance we say it is homogeneous. So, what is the working substance? Working substance are nothing but they are chemical reaction products. So, basically they are combustion products. So, they are homogeneous. We can consider that all the working species are gaseous. Now, there is a chance that the species can be in the form of some condensed phase, there may be some liquid or solid phases of combustion products, but for our assumptions we are considering that all the species are gaseous. So, any kind of condensed phases are kind of negligible. Of course, one can argue on these things that how can we consider this one, because if you see, if you consider a solid rocket, if this is the typical solid propellant rocket, it consists of the propellant grade. In the propellant grade, if you look it very closely, it consists of various metal particles as fuel. It may have it must have the oxidizer crystals. So, if we consider these are aluminum particles, the bigger one if we consider they are ammonium perchlorate, those are crystals, and they are bounded together with the help of the HTPB or the polymer. So, once they burn, they will create the combustion products which will go and expand in the nozzle. So, according to our assumptions, we are considering that there will be no condensed phases present in the product, but there is a possibility that some of these aluminum particles will convert into aluminum oxides. So, there is a chance of some of these small oxide particles present in the gas, and maybe there will be some, if the temperature is not high enough, if it is not more than its volatilization temperature, they may become some molten oxides. So, it is possible that some of the phases are liquid, but for the sake of simplicity, for the ideal rocket concept, we are considering that all gases, all species are present are gaseous. So, this is another assumption. Now, once we say all species are gaseous, we also say that our working substance obeys the perfect gas law. This is a straightforward assumption. We say that no heat transfer across the rocket walls. So, in a sense we say the flow is adiabatic. Okay. So, this is another assumption. I think many of the assumptions you have already learned during the aerodynamic course, if you have taken like while considering the isentropic flow through nozzle, some of the assumptions we have already learned there, but I just want to repeat those just to start the course with a background that we already familiar with these stuffs. Number 5 assumption is there is no appreciable friction and of course, plus no boundary layer effects. We consider that there is no shock wave or flow discontinuities present in the nozzle flow. Again, probably you have already done this thing in your previous aerodynamics course, that this assumption was already there. So, probably you have considered that. We consider that the propellant flow is steady and constant, is steady and constant. Now, if you look at the previous slide here, what we are saying propellant flow means the whatever the propellant is burning there will be some mass flow rate, like let us say m dot f for solid rocket. So, there will be some burning of the propellant layer and they will form some product gases. So, it will be some regression of the propellant. So, that will form the combustion gases after burning. So, we say that the propellant flow is like constant and steady. Same thing applicable for the liquid rocket, because liquid rocket it is coming from two separate tank, fuel tank and oxidizer tank. They are passed through some pump and they are coming to the thrust chamber. So, what we are saying through this assumption that the propellant flow is steady and constant. The transient effects, like during the starting and stopping, there may be some changes in the flow rate of course, but we are neglecting the transient effect. So, we are neglecting the transient effect such as during starting, during start or stop. One more assumptions we already considered while we learned about the isentropic flow through nozzle, which is like the exhaust gas leaving the nozzle is axial, means it is following like one dimensional nature. So, what I am saying here is, if you look at the nozzle here, we are saying the flow is axially directed, means one dimensional. But if you look at very closely near to the wall, the flow cannot be exactly axial, because it is going to follow the like this. So, the assumptions we are making here, that all the gases are flowing through the nozzle axially or it is parallel to the nozzle axis. So, one dimensional flow is considered. This was already there, if you recall recall the assumptions used in the isentropic flow through nozzle. So, it is the same assumption. Now, we also consider the gas velocity, pressure, temperature and density are uniform across any cross section. Any section normal to the axis. What does it mean? It means, let us say if we consider our section here like at A, B, B. So, at any section, if you look at, there are various locations like at different radial locations. So, according to these assumptions, the gas velocity, pressure, temperature and density are uniform across any section normal to the axis. So, if I say the velocity at this location and this location are the same, although there is a radial it is radially at different location. So, this location is not the same location as this, but however, since we are considering one section normal to the axis, we are considering at this station, at station A, the velocity, pressure, temperature and density are uniform, whereas same thing at station B, the velocity here and velocity here are the same. So, this is another assumption. So, it is almost similar. If you recall, you have done some cycle analysis for air breathing engines like turbojet, turbofan. You have considered the pressure, temperature at different locations, like at the compressor inlet, at the compressor outlet, at the combustor outlet, at the turbine inlet, at the turbine outlet. You did not consider the effect, the change of pressure, temperature at different radial location at the particular section. So, it is a similar type of assumption. And also we say that the chemical equilibrium is established. We say that there is no further change in the gas composition, whatever the gas is passing through the nozzle, there is no further change in gas composition. So, there might be some reactions taking place in the nozzle itself, but we are not considering that. Even if it is taking, we are considering it has a negligible effect on the species composition. So, we say the chemical equilibrium is established and no chemical composition is going to change during the course of the gas passing through the nozzle. Okay. So, these are the various assumptions and some other assumptions which allow us to do some simplified analysis and make the equations, I would say represent the equations in a more simple mathematical terms, through which we can actually do the calculations. Having said that, we can begin our derivations, what we have already learned about the Vj. If you recall, our important terminology in the rocket equation was delta V into Vj ln mi by mf. So, we said that we should at least look at what are the influencing parameter which are affecting Vj. So, let us try to derive this. So, what we need to consider here is that the flow through nozzle. So, nozzle is nothing but just a vent. You can say one high pressure, high temperature chamber is there, where so we can consider expansion of gas from a high pressure chamber. Basically, we can treat one high pressure chamber, you can take any shape, does not matter. So, if you look at the nozzle, it will take like this. So, basically we can treat this the same thing as if like it is a high pressure chamber with a small vent. So, this is the vent. So, if you consider a control volume of this vent, you can actually apply the if you consider the inlet and outlet condition of the vent. So, let us say we have the chamber condition like the HC, PC and TC. So, enthalpy is HC, chamber pressure is PC, chamber temperature is TC. At the exit we can say, we know already the velocity is Vj, we can consider the pressure PE, enthalpy HE. Now, if we just apply the steady flow energy equation for this control volume, what you can write here is, let us say if we consider that there is a heat input and work output by this control volume. So, if the heat input is Q dot, work output is W E, we can simply write the HE plus Vj square by 2 plus some potential datum if you consider the effect due to difference in the height JD let us say, minus we can say the inlet condition, which is Hc plus Vc square by 2 plus GZC. Okay. Now, here m dot is the mass flow rate through the nozzle. Hc, we have already said the Hc and He are the enthalpy of gas in the chamber. Here it is in the chamber, here it is at the exit of the nozzle. Jd and Zc, we have considered that heights above the datum at entry and exit. You know, we have already considered the adiabatic flow. So, we can take out this one to 0. There is no work. So, we can consider this as 0. So, eventually this equation will become this equal to this, and also the difference between the Jd and Zc are minimal. So, we can take out these two terms also. Now, further we can see that the velocity Vc is kind of very small compared to the velocity of the velocity at the exit. So, this can also be kind of a negligible, okay, because in the inside the chamber flow is almost like a having the negligible velocity. So, eventually this equation will become Vj square by 2 equal to Hc minus He. Okay. So, if you expand this further, we can write this in terms of Cp Tc minus Te. Remember, we had begun this exercise just to know what are the influencing factors on the efflux velocity Vj. So, we are trying to write Vj in terms of other. So, we can simply write Vj square equal to 2 Cp Tc minus Te. So, we can again we know what is Cp. Cp we can write 2 into gamma universal gas constant Ru by molecular weight. We can write molecular weight into gamma minus 1, because Cp we know Cp equal to gamma R by gamma minus 1. Then we can write Tc outside 1 minus Te by Tc. Okay. So, one can write here. Now, one can do further simplification. So, remember what we have write here is we have written Cp equal to gamma Ru by molecular weight into gamma minus 1, because R for that particular gas is Ru by molecular weight. Okay. So, this is the universal gas constant, which is given as the 8.314 kilojoule per kilomole Kelvin. So, if you know the molecular weight of the particular gas, you can easily find out the universal you can find out the gas constant for that particular gas, because if you have to apply this equation, you need to find out the value of R. Now, one can actually think in terms of the isentropic flow, and we can actually simplify this equation further by considering that this Te by Tc we can write in terms of the pressure ratio P by Pc to the power gamma minus 1 by gamma. So, applying this relation, we can modify this equation and we can write Vj square, or we can directly write Vj as square root of 2 gamma Ru Tc gamma minus 1 into molecular weight into 1 minus P by Pc to the power gamma minus 1 by gamma. So, this is the equation for the efflux velocity or the jet velocity. Now, in the next lecture, we will try to understand what are the parameters which are more important and influencing the value of Vj, because that Vj is very important in terms of the rocket equation. So, we will try to understand the various influencing factor for Vj. With that, we close this lecture. Thank you.